Let's talk about multimeters. The multimeter is one of the most important tools that you can use for your electronic projects. We're going to talk about not only the different types of multimeters, the different functions that they have, but also how to use them and a little bit better understanding of what to do with a multimeter. In front of me, I have a few different multimeters that we offer here at SparkFun. You've got the standard portable handheld type like this, and then you also have the tweezer style, which looks a little something like this. Each one has their particular pros and cons. Mainly, it comes down to form factor. This one's going to be a lot easier to use on in circuits, so actually, using it on the PCB directly, whereas this one's going to be just a little bit more good for general use. But as we get into the features and what these actually do, it'll become a little bit more apparent on why you would choose one over the other. Before we get started measuring continuity, let's talk about the probes. The two meters that we have here and here both come with their respective probes. These are the probes for the standard, and these are the probes for the nicer meter. During all your adventures with the multimeter, you might be measuring all sorts of different items, anything from a PCB to a battery to any of these other discrete components. The jacks on the multimeter use standard banana plugs, so anything that has a banana plug on the end of it you can use into your multimeter. These are little IC hooks. These are nice for connecting to really small leads like on this little dip, and we can connect and we don't have to worry about touching the leads next to it. Another thing that you could use is these little guys. These have alligator clips on the end, so if we're attaching to something larger and we don't want to sit there and hold the leads in place, like, I don't know, maybe this audio jack for instance, we can actually just directly attach to one of the wires, and then it frees up our hands to do something else. The end of these banana jacks have two different holes in them. They're no accident. They're made for plugging in additional banana jacks either into the top or into the side. That means that you can leave the ends of these in your meter and actually stack additional ones on top of it, so we can quickly go between the IC hooks and the alligators if you want. If you're looking to measure SMD components, you have two options. You can get a dedicated meter like this one that we showed earlier with the tweezer tips on the end, or we also sell this little device which plugs directly into the multimeter and gives you the same functionality as the tweezers. One of the most common things that you're going to do with any meter is measure continuity. Continuity is very simple. Continuity tells you if the circuit is closed or open. So if we take a length of wire, put the probe on one end, put the probe on the other, it should be a continuous circuit and the meter will beep or show some sign that that is a closed circuit. However, if the circuit is open, the meter will do nothing to indicate that it is not an open circuit. This is really useful for testing if there is a short between the ground and the power, or testing if there is continuity between the ground planes or between the power planes. So if we want to test if a circuit is open and won't work, or if it's shorted out somehow before we turn it on, continuity is a great way to do this. We're going to be using this cable in a later demo. Now, I didn't do my homework and I didn't check which one of these wires go to which jacks on the end of this. So continuity is the greatest way to test this, and you're going to be doing this all day with a meter. What we're going to be using primarily is going to be the milliamps and voltage and ohm. That symbol stands for resistance. So we're going to be placing the red lead here. We will get to this jack later, but that is going to be used for high current measuring. For most of the testing, you're going to have the black lead into COM, the red into this jack here. Turn the meter over to this little sound symbol. This is going to be the continuity test. And the reason it has a little audio symbol next to it is when I touch the leads together, we hear this noise. This other meter operates pretty much the same way. We're going to attach the black lead into the COM, and we have a few more options here. But if you look down, we've got voltage, resistance, hertz, temperature, and that is a symbol for a diode. And we have all the current listings over here. So we're still going to use these two. So we're going to attach in the COM and attach over here. When we turn the meter on, the display turns on, and we use this button down here, once again with the audio symbol, to cycle until we see the symbol show up. It's right there, and it works the same way. I'm going to start at the innermost lead, and for testing continuity it doesn't really matter which one is where. Ultimately we're just checking to see if the circuit is closed. So I'm going to just use this over here. And so we can now tell that this first innermost ring is attached to black. As you can see, just brushing up against this wire doesn't actually close the circuit. So this is actually a good reason why it might be nice to use one of these alligator clips. So it actually makes testing a lot quicker and more reliable. There we go. So let's move on to resistance. Resistance is quite simply the amount of resistance that the electricity flow has. This demonstration is going to show the difference between the entry-level meter and the slightly higher-end meter. This one is what we call an auto-ranging meter, meaning that it ranges the value based on whatever it sees. So if it sees a 10K, it says, hey, it's a 10K. Whereas this one, you actually have to set the adjustment range, and it will display based on what range you have. On the dial, we can see this symbol, which is the ohm symbol, and we see all these different ranges here. We've got 20 mega ohm, 200K, 20K, 2K, and 200. The reason these numbers are spaced out the way they are is the leftmost digit on this display is a 1. So that means that we can go up to 20 mega ohms because that is limited by the display ultimately at 1999, whatever. So if we go down to 200, this can read up to 199 ohms. If we have a higher resistance value than that, then we need to go up to 2K. So just for the sake of this demonstration, I'm going to start at 200 ohms. And I've got two different resistors here. I actually don't know what value they are, so we're just going to, try and figure out what the resistance value is. So I'm just going to attach my leads on either side just to be hands-free. And we see that once we attach this, we've got a 1 and a dot. This means that we're outside of the range. It is greater than 200 ohm. So I'm just going to move this dial up. And now we're on the 20K. So that means that this is in the 20K range, and it's a 3.27. This is a 3.2 kilo ohm resistor. For this resistor, we're actually measuring 0.009 ohms. So that's actually really low. So this is a small fraction of 20K. We're inside the range, but it's just really low, and it's going to be hard to read this. So what we're going to do is switch down the range, and you'll see that it increases. And as we go down to the 200, so this is a 99.5 ohm resistor, or about 100 ohm. So this is how you use a ranging multimeter to test resistance. On the auto ranging meter, let's turn it on, and we're going to use the center button to cycle to the ohm resistance right there. And there it is, so it pops up, and you can see that it has an M and a K as it's searching. It will actually tell you the range. So I'm just going to take these leads out for simplicity, plug them in. It's going to find it. Boom, 99.6, 99.10, 100 ohms. So this meter, we don't have to do any ranging, nothing. All we do is plug it in, and it tells us the value. Let's talk voltage. Both of these meters can pretty equally measure both AC and DC voltage, so let's do just that. For either of these meters, we're just going to select the voltage range. You see the little squiggly guy, that is AC, and the straight is DC. The straight means that DC is a constant direct current, whereas AC is variable, so it has a little squiggle next to it. So we're just going to go ahead and select 20 because our 9 volt is below 20. And we'll just go ahead and measure this. I'm not going to care which lead is where. And you can see we're getting negative 8.95. That means that our leads are actually switched around. This is actually the positive or the red lead. So if I switch them around, there we go, positive 8.6. So it really doesn't hurt anything, but you're just going to get a negative or a positive reading, and batteries are going to be positive. And in much the same way, we just select the voltage over here. You can see AC and DC, and this will auto range, and there is our voltage. So it's pretty easy. Now, these meters can handle a pretty sizable voltage. I think both of these are up to 600 volts, so you shouldn't worry about what cell you're using it on. They should be able to measure just about anything. So this is a 3.29 volt cell, and you can see that it's negative. This one doesn't really have any obvious markings, so if we wanted to just do a quick test, we can actually use that negative symbol to detect which one's positive and negative. Now, let's measure AC voltage. Here we've got a power strip, and this is plugged directly into the wall. I have my probes jammed into the power strip like that, and as you notice, I am not touching anything. There is nothing exposed here. We still do recommend not trying this at home because this is AC voltage. It is very dangerous. Here I've got my meter set to the 200 volt range because we are here in America, so this is going to be 120 volts. And when I flip this switch, let's see what the meter does. There you go. We're measuring just over 120 volts AC. I could do the exact same demo with this meter. We're going to get the same results. So let's use some of the more advanced features that this meter has that the basic one does not have. This meter will allow us to measure lower voltages of AC a little bit more precisely, like the AC that comes out of a phone. So you might be thinking AC comes out of a phone. Well, out of the audio jack, audio signals are actually AC. So we can send an audio signal out of here, measure the amount of voltage coming out of it, and additionally, we can actually use the hertz to measure the frequency coming out. So I just have a little simple tone generator set up here. I'll plug in my leads. We will turn on the meter, and first I want to measure the amount of voltage. So I will cycle over to AC, and this will auto range. And remember when we toned out this cable earlier, we found out that these two pins are the ones I'm concerned about. We'll plug in and do some white noise. And there you go. We're at 0.35 volts. So that's how much AC voltage is coming out of this phone. Now I want to measure the frequency. We have the frequency set for 4.26. White noise is full spectrum, so I'm going to switch over to a sine wave and then click on this button, which is the hertz. As you can see, we have it set at 4.26K, and we're getting almost exactly 4.26K out of here. And if I were to turn this off and adjust the frequency to a little over 1K, you can see 1K. Let's talk diodes. Diodes are one-way devices. Earlier we talked about resistors, continuity, and those are components or concepts that do not necessarily have polarity. It doesn't really matter with the positive or negative, but there are certain components where positive and negative or the direction of the current flow matters a whole lot. Diodes are an example of that. LEDs are diodes. On a schematic, you might see a diode represented as a triangle with a line over it, and that means that the current can only flow one way, and if it tries to flow the other way, it does not allow that to happen. Multimeters are great for testing the direction of a diode. If you have a diode and the label is worn off or you don't know which direction it is, you can use a multimeter to test that. It actually just puts in a small voltage, and then you can test the directionality of that component. Also, you can use that to test out the polarity of an LED, as I will show you. I'm going to start with this diode. You can see there's a little white line on this. This is just a classic signal diode used in power rectifiers, things like that. And you can see this white line lines up with the little diode symbol right there. It means that power will flow this way, but not this way. And as we know from red and black, or positive and negative, power will flow from positive to negative. So if I hook this up this way with the positive on the side that the line is on, and to negative, I am assuming that the power will flow this way, and because of the diode, it should not. So if I hook this up, I see no change on the meter. Now if I were to reverse this diode, I read something. So I can actually detect not only if this is a good diode, but that it is connected the correct way. Now, LEDs are diodes as well. What's going to happen if I connect a LED in the same way as a diode? Nothing happens that way. Oh, it actually lights up. What's happening is a small bit of current is actually flowing through the diode from the meter, because the meter has to supply something into it to tell if it's hooked up the right way, and we actually get it to light up. So this is invaluable for not only testing the correct polarity of an LED, but also to test if your LEDs are still working. Another classic function of the multimeter is measuring capacitance. This is a feature that you will only find in the higher end units and not in the more basic units. Measuring capacitance is relatively rare, but it's still useful to have. For these little capacitors, they don't really have a whole lot of writing on them, so sometimes it can be very difficult to tell what value they are, especially when a bunch of them are thrown together. So having a capacitance meter is really handy. And here we can see that is 9.23 microfarads. So pretty easy. One thing to note with larger capacitors, especially electrolytics, they do take a few seconds to actually charge up and for the meter to read them. So, give it a couple seconds, wait for the meter to stabilize. And here we can see this reads 95.6, and this is a 100 microfarad cap, so we're pretty darn close. Another feature about a higher end meter is the ability to measure temperature. The 70C auto ranging meter comes with this little temperature probe, which plugs directly into here. So plug in that, and at the end of it, it has this little tiny thermocouple thing, and it measures the voltage coming off of this and calibrates it, and we get a reading. So we're going to hold down on this button here, and then that has the Celsius, but we're in the United States, so we're going to go with Fahrenheit. And you can see that it is about 73 degrees in this room, and as I hold on to this, instantly warms up. Let go, blow on a little bit, and we can cool it down. Current is the last thing that we're going to show you how to measure with a multimeter, and current works a little bit differently than everything else. As before, we were probing into a complete circuit and measuring a value based on that. With current, however, we actually break that circuit and interject the meter into it. For instance, if I have a closed circuit like this, power flows around like that, we don't really just put the meter into there, because then we're putting current into the meter, and that's bad. What we actually need to do is break that circuit, put the meter inside of the circuit, run the current through it and back out, and that is how we measure current. So it works a little bit differently. Let's measure it with both of the other meters. I've got a couple of motors and a power supply. Let's see what kind of current we can measure. I'm using a benchtop power supply for my power source here. The added benefit is I actually can check the current meter on it just to verify that we're doing the right thing, just to give you an idea how that all works. We've got two different motors. I've got a really big one right here and a smaller one. Meters have two different ranges on them, and this is the reason for all these different jacks at the bottom. If we look at the basic one, we have a 10 amp here, and then over here we have a 200 milliamp between here and here. So if I'm using the small motor, I want to measure here, and it has a max of 100 or 200 milliamps. And if I'm measuring beyond that, like this bigger motor, I'm going to want to measure over here. And in much the same way with this, I actually still use the COM, but if I'm going to do anything with current, I actually want to measure over here and here. This one being 600 milliamp and this one being 10 amp. So they both have roughly the same range to them, they just have slightly different configurations. We want to create a circuit that goes out from the power supply into the motor, through the meter, and then back into the power supply so that we can measure the current through this system. So I'm going to start by plugging into the negative side of the power supply, into one side of the motor, then into the other end of the motor, which will then go into the meter, out that meter through this jack, and then back into the power supply. So for that, I'm just going to connect these together and then back into this power supply. So that is my loop. So when I turn on the supply, I should see the current measured here with a maximum of 200 milliamps. Now you can see that we're peaking out a little bit, and if we look on the meter, we are peaking a little over 200 milliamps, so I can limit the current just a tad. But that is measuring right at 200, 190, 180 milliamps. So I'm going to go ahead and turn this off. And what I'm going to do is I'm going to move over to the 10 amp jack. And so this should allow us a little bit more room to measure. And I'm going to keep it at the 200 for right now. You can actually see it moves a little faster because we're less restricted. And if I move it over to the 10 amp, this matches exactly this range. Here I have the auto ranging meter set up, and you can see that I have the black wire in the COM, and I have this guy in the milliamp, which is up to 600. So it actually gives me a little bit more range than the basic meter at only 200. This meter has an interesting feature which works really well for this setup. Down here we actually have a little graph that can show the minimal fluctuations that happen. This is similar to an old school analog meter that would have the dial that would kind of flutter. Digital displays really don't update fast enough, and it's too hard to see little fluctuations, but this little meter at the bottom will allow you to see that. So when I turn this on, those little fluctuations that you were seeing will be a little bit more apparent in that meter at the bottom. So you can see down there we have these little fluctuations, kind of like a little VU meter that shows the little variance that we have in the current. And of course, if we hold on to the output of the shaft, you can see that when I squeeze down, that little meter jumps up and down. Now we have the much larger motor hooked up and we're using the 10 amp jack on here. Another feature about this meter is that it has a range button. As I said before, this is auto ranging, but if we use the range button, we can select the range that we want. For this case, maybe I want to see 3 decimal places instead of having only 2. Or I can have 2 decimal places. So we can actually switch the range around and have it fixed on that range so that if it fluctuates around, we have it fixed on a certain value. So I'm going to turn this one on and we'll see what happens. So we're about, half an amp, and as I slow it down, you can actually see it jump up.